Am I audible?
Yes, ma'am.
Okay. Yesterday we started with this bistable. Okay, so I will just do a quick revision. So a combinational logic circuit, it is a like it doesn't have an input. It only has an input and output, and it doesn't have a feedback. Okay, so like I gave an example of AC, like it doesn't have a memory. So and output is not affecting the input. So you have to change it manually. Okay, so examples of this combinational logic circuit is adder, subtractor, decoder, and multiplexer. Whereas in a sequential logic circuit, we have an input and we have an output, and there is a feedback. So we have a memory element. So it remembers what is the previous state of the output, and here the output is affecting the input of the circuit. So this is the sequential logic circuit. So examples are counters and registers. So we will be studying this in the next class. So the basic of this bistable is the NAND gate and the NOR gate. So we will see the truth table of this NAND gate. What is the truth table for NAND gate? We are getting as 1110. But mainly we are using this truth table 00 and 11. 00 and 11 condition for both NAND gate and also for NOR gate. So the truth table is 1000. So the inputs we are using is 00 and 11. For 00 we are getting a 1, and for 11 we are getting a 0. So these are the basics of bistable. So what is a bistable? We are calling it as bistable because we here there we have bi. So bi means two stable states. Okay. So what is first stable state? It is logic one. As we are using binary, so there will be only two stages. One is one and one is zero. So one we are calling it as set, and zero we are calling it as reset. Okay. So it has two stable states. So here it will remain in the same state until and unless uh, a signal is applied in order to change the state, or until the supply is disconnected. So here it will remain in the same state. This is for flip flop where we are using clock. So until and unless we put a clock, then the output will change, otherwise it won't change. So this is only applicable for this clock state. So bistable thus constitute a simple memory cell. So this is bistable is the basic of how we are creating a memory cell for a digital devices. So that's why we are calling that as memory cell. So here in bistable, we have two complementary outputs, which are Q and Q bar. So we are calling it complementary because if Q is 0, then we will get a Q bar of 1. So that's why it is called complementary, or we will can also call it as inverter. And if we are getting Q as 1, then we will get a Q bar of 0. Okay, but here I am specifying this Q is the main output. This Q bar is not the main output. Whatever is the state of Q, that will be the output. So if Q is 0, then we will call it as reset, and if Q is 1, then we will call the output as set. Okay. So this RS bistable is the simplest form of bistable. Okay, we have input of S and R, and this is the diagram. So we have input as S and R, and we have two outputs Q and Q bar, which are complementary to each other. So we will see how it will work. So bistable will remain in the present state until unless we change the inputs of the circuit. So as I told, we are making this bistable either with NAND gate or we are making it with NOR gate, but mainly we are using this NOR gate. Okay. So see, remember the outputs of this NOR gate. Whatever the NOR gate is, that is only the output. So this is our main output. NAND gate, we will just study what is NAND gate, how we are using this bistable through NAND gate, but this NOR gate is the main, and this will also come in exam. So here we have set and reset. So here we put set at down in the second NOR gate, and reset we put it in the first NOR gate. So these are the inputs, and the output for this first NOR gate is Q, and output for the second NOR gate is Q dash. So remember, this set is down and this reset is up. Okay, don't reverse this. And we can see the output for this first NOR gate is going back to the input of the second NOR gate, and the output of this second NOR gate is going to the back to the input of this first NOR gate. So that's why we are saying it as the sequential circuit, because output is affecting back to the input of this this gate, this bistable. That's why it is called a sequential circuit. Okay. So this is the truth diagram. So this first case is the memory. So we will see this case afterwards. We will first go to the second case and see how is this second and third case working, and then we will see how what is memory. Okay. So we will simulate this in Logisim. So this is our circuit. This is our set. This is our reset, and we have output Q and Q naught. Okay. So we will say the second condition of 0, 1. Okay. So set is 0 and reset is 1. So we will always start from wherever we are, the input is 0. Okay, always start from that side. So if we see the second NOR gate, we can see the inputs are 0, 0. So for NOR gate 0, 0, we are getting an output of 1. So here, that's why we are getting an output of 1. If we go back to the this NOR gate, we can see for 0, 0, we are getting a 1. Okay, so that's why we are getting a 1 over here in the Q bar. And if we see the inputs of this first NOR gate, we can see it is 1, 1. So if we see the truth table for 1, 1, we are getting a 0. So that's why we are getting a 0 at the Q. So Q is the main output. So Q is 0. It means our system is reset. Okay. That's why here we can see for 0, 1, we are getting a Q and Q as 0 and Q bar as 1. So we are calling it as reset. And then we will see the memory state. What is a memory state? So if we put the condition after any output, if we put the condition of S is 0 and R is also 0, then we will see that the output, it is not changing, means it remains Q and Q bar. And here we have written it as Qn plus 1 and Qn plus 1 bar, because this is the next state. Okay, that's why we are writing it as n plus 1 and this as n plus 1 bar. And here we are writing Q and Q bar because this is the present state, or if we call it as a this way, if we call it as present state, then we will call this as past state. Whatever the past state was, we will get that. That's why we are writing it as n plus 1. So remember this output, we have Q as 0 and Q naught as 1. So we will test the memory state. Okay. So if we do this as 0, 0, then the output is not changing. Means it is remembering what is the previous output and it is showing that that output only. So this is called as memory state. Means our output is not changing, or the device is storing the previous outputs. So this is the memory state. So this is the basic of how we are using a memory in our digital electronics. Okay, this is the basic. So if we see the case 3, so our S is 1 and R is 0. So here our S is 1 and our R is 0. Then we will always start from wherever we are giving input as 0. So for 0 0 we are getting a output of Q as 1, and here the output of Q, here it is going back to the NOR gate, second NOR gate. So we can see here the inputs are 1 1. So for 1 1 NOR gate the output is 0. Okay, so here we are getting Q naught or Q bar as 0. So here in the truth table for 1 0 we are getting a Q as 1 and Q bar as 0. So main output is this Q, so we are calling the system as set. Okay, then again we will test this memory. So what is this memory? If we put S and R as 0 0, then we will say that the next state will be the output will be present state, or the present state will be our previous state. Okay, so if we put it back to set as 0 and R as 0, so we can see that this Q and this Q naught, it is not changing. That's why it is a uh, that's why it is called a memory cell, because our Q and Q naught is not changing and it is remembering the previous state, whatever the previous state was. So the output is the same state. So that's why we are calling it as memory cell. Okay, any doubt in this memory state?
No, ma'am.
No, ma'am.
So this is our main circuit. Okay, we are using RS bistable for every other states, for D flip flop and for JK flip flop. We are using this basics of this RS SR bistable. So remember this. We are not using this that NAND gate. This NAND gate is only for reference. So So whatever I have explained, it is shown over here. So we are first testing this case 2. So we are putting it 0, 1. Then again we will test this case 1. So if we do 0, 0, the output it remains constant. And here is a case 3 where we are giving 0 1. So we are getting a 1 0. So we will again switch it back to this case 1 and we will put it as 0 0. Then we will see that the output it remains constant. So this is a memory state. So this is the operation of RS bistable. Okay. So here, what if we do 1 1? So if we put here 1 1, then we can say that Q and Q naught we are getting it as same. So here Q and here it is Q naught or Q bar. This should be always be opposite, but here we are getting same Q and Q naught, so this condition is invalid. Or if we do it in logic simulator, we will see that this will toggle, this Q and Q naught, it will start toggling. I will just show you one video in that students have done the experiment where it is toggling. Have to search for it. So give me 1 minute.
Okay, ma'am.
I don't think that is captured. See, here, if we do 1 1, this starts toggling. It cannot decide what is the output. Okay, that's why it is switching on and switching off. So this is called toggling. Okay, so this is how it is working. Like it will, if we do 1 1, then it will start toggling. So this is how our bistable is this 1 1 condition is becoming invalid because it starts toggling. It cannot decide what is the output. So that's why our this condition 1 1 it is invalid. Okay, you can see how it is toggling. So this is called toggle. It is switching on and switching off. So that is called a toggling. That's why our condition this 1 1 is invalid, because this q and q naught it cannot decide, because if you see the output, so this is becoming uh, so actually it is becoming 0, so it becomes 1 0, so we are getting a 0, and here we get 1 0 1, but these are constantly changing because of the NOR gate. So that's why it is actually toggling. It cannot decide what is the output. If you do on some another condition, it will come as 1 1. So that's why it is toggling. It cannot decide what is the output. So this 1 1 condition is becoming invalid. So this is another bistable for we are using NAND gate, but because we are using S and R for this NOR gate, that's why for NAND gate we are using S bar and R bar. Okay, so here earlier we had set, and earlier here we had reset, but because this is S bar and R bar, that's why we are using this as S bar. So this is becoming our set, and here we are using R bar, and it is becoming our reset. Okay, so here also we will see three conditions for case 1, case 2, and here 1 1 condition is the memory condition. Okay, so we will just see how the circuit is working for 0 1. So we have put S as 0 and R as 1. So S bar as 0 and R bar as 1. Okay, so here I have written S naught. So S naught as 0 and S bar as 1. So here we will always see the condition where we have 0 0. Okay, so for if we see the output for this NAND gate, so for 0 0 we will get a 1, and for 1 1 we will get a 0. So for uh, 0 1, I told you for 0 0 we will get a 1, and for NAND gate 1 1 we will get a 0. So as set, S bar is 0 and R bar is 1. So here we will get Q as 1 and Q naught as 0. Okay, so this is the truth table for this first case. We are getting Q of 1 and Q bar of 0. So as Q is 1, that's why we are calling it as set, because Q is the main output. Okay, then we will test this case 3, which is the memory state. Okay, so if we do 1 1, then we will see it will be the previous output. So for we can see Q is set and this Q naught is reset. So our system is set. Okay, but if we change back it to 1 1, then we can see this Q and Q naught, this is not changing. So this is our memory state. Okay, this Q and Q naught is not changing. And if we check for this condition, case 2, S bar is 1 and R bar is 0. So our output is 0 and 1. So S bar is 1 and R bar is 0. So we can see here we are getting 1 1. So that's why we are getting a Q of 0. And here in the second NAND gate, we can see the inputs are 0 0. That's why we are getting a 1. Okay. So for S bar as 1 and R bar as 0, we are getting Q as 0 and Q bar as 1. So this is what it is written in the truth table. Q we are getting it as 0 and Q bar as 1. So because Q is the main output, we will call it as reset. So again, we will check this memory state, which is 1 1. So if we do S bar as 1 and R bar as 1. So we can say that this is not changing. Q was 0 and Q bar was 1. So this is called memory state and how we are storing the data. Okay, using this memory state. So if I do 0, 1, then we can say we are getting 1 and 0. And if we revert it back to 1, 1, so this state is not changing. And if we do it as 1, 0, then Q is 0 and Q bar is 1. And then again, if we do 1, 1, this Q and Q naught is not changing. So this is a memory state. And here this 0, 0 condition is invalid. So if we do 0, 0, we can say this Q and Q naught, we are both getting it as 1. So this Q and Q bar should be opposite to each other. And so because of that, this condition is invalid. And if we do it in any other simulator, we can say this Q and Q naught, this will again start toggling. It will keep on switching on and switching off. It cannot decide what is the output. So this condition is invalid. Okay. So any doubt in this RS bistable and S bar R bar bistable? Any doubt in this? Okay. So we will go further. So what are the shortcomings of SR bistable? So in this simple cross couple bistable has a number of serious shortcomings. Consider what would happen if we give a logic 1 simultaneously present on the both set and reset inputs. So this is for NOR gate. Okay. So if we are giving it as S and R as 1, so we can say that the output is not stable and both are getting we are getting Q and Q naught as 0. So this condition is totally invalid. So that is the shortcoming of SR bistable. And that's why we are using this D and JK bistable. Okay. So practical forms of bistable make use of so much improved purpose design logic circuit such as D type and JK type bistable. So that's why we are using this D type and JK as bistable state. And here one more problem is that here we have two conditions of 0 1 and 1 0. So why to use two inputs here? We can simply use one input. So that's why we are using this D bistable, because either S is 0 and this R is 1, and S is 1 and R is 0. So they are inverse and this last condition is not working. So we can simply use one input and just we can use an inverter for this. So we will go to this D bistable. So what is this D bistable? So D bistable is two in has two inputs. Both are actually same inputs. So here our D is standing for either data or delay. So here we have D type. So it is either data type bistable or delay type bistable. And here we are introducing a clock. Okay, earlier we were not having any clock. So this is a clock we are using. It is same as a digital signal. It is of consists of 0 and 1. So if we consider this side of the clock, so it is we will call it as rising edge. And if we consider this side of clock, so we will consider this as falling edge. Okay, because here it is rising and here it is falling. So that's why we are calling this as rising edge and this as falling edge. And this is not in syllabus, but we are saying what is rising edge and what is falling edge. So that's why I'm telling you what is rising edge and what is falling edge. So here also D-type bistable is modified set register bistable with addition of an inverter to prevent SR inputs from being the same logic level. Okay. So here we have put an inverter. So instead of two inputs of S and R, we have only used an inverter, and we have added this clock. So D bistable uses, it can be it. These are the applications. So D bistable are used both as latches, a simple form of memory. So previously SR latch, so that is we are using it as memory. So that is this first application, and it is can be used as a binary divider. So this we are not studying, but these are the two applications of this D bistable. So how is this D bistable working? So data inputs of logic 0 and logic 1 is clocked into the bistable such that the output state only changes when the clock uh, changes the state. So from bistable we are studying that the output won't change unless and unless until and unless we will change the clock. So that is what this it is how it is working in this D bistable. Okay, the output it won't change unless we change this clock. uh, Whenever we will put a 1, only then it will change. So this is what we are saying in the bistable. Okay. So we will see how this D type bistable is working. So this is a D bistable and this is the input, and here we are giving a clock. So we can put clock as 0 or 1. Okay, and here we are giving a D as 0. So if we give D as 0, so this will become this first condition. Okay, so for if we give D as 0, then we can see that S here our S. So here we can see if we give D as 0, then here our S will become as 0, and because there is a NOT gate, this R will become as 1. Okay, so here it will become S as 0 and R as 1. So it is same SR latch. So we are using this as NOR gate. Okay, remember this, we are considering this NOR gate. So for this condition of 0 and 1, we can see the output where at Q we will get as 0, and for Q bar we will get a 1. So as Q is 0, so we will say that system is reset. So if we give D as 0, so our S is becoming 0 and R is becoming 1. That's why our Q is becoming 0 and our Q bar it is becoming 1. Okay. So this is our second condition. Then we will see this third condition where our S is 1 and R is 0. So if we give D as 1, so our S becomes 1, and because there is a NOT gate, our R will become 0. Okay, so we will get a 1 and 0. This is using our SR NOR gate because it is SR. Otherwise, it would have been written S bar and R bar, but here it is SR. So we will consider this is a NOR using a NOR gate. So if we put D as 1, so you can say this output is not changing. So I told you until and unless if we change the clock, the output won't change. So if we change the clock, only then our output will change. So this clock has to be 1. Okay. So here you can see the clock has to be 1. Only then our output will change. So this is the main output. Here we are getting Q as 1 and Q bar as 0. So this is the main output, and because Q is 1, so we will say that the system is set. Okay, then again if we change the clock, you can say, see, this is not changing, the output is not changing. So this is the final output. Okay, because the clock is not changing. So how can we say that memory will work? So if we put this clock as 0, so that is considered as a memory state. So if we put a clock as 0, we can say this Q and Q naught is not changing. So that is a memory state. And if we do D as 1, D as 0, then again we put the clock as 1, then only our output is changing. And if we put back it to 0, so we can see that the output is not changing. So it means that it is a memory state. Okay. So this is the final output. Even if we change the clock to 0 to 1, then it is not changing. And if we put this to 1, so this is the memory state because clock is 0. And if we change it back to 1, only then the output is changing. So this is what we are calling the until and unless this clock changes to 1, our output won't change. So this is how we are saying that this is working. Any doubt how we are working of D bistable?
No.
So this is D bistable, but here also we can say we have decreased the inputs, okay? But then also this 1-1 condition, that is becoming invalid because we can't do 1-1 because if I do 0 or 1, either 1 will become 0 and 1 will become 1, or S will become as 0 and R will become as 1. So this condition, we can't do this in this D bistable. But here what we have done, we have reduced the number of inputs. Okay. So this is the truth table diagram for D bistable. So here I will explain this truth table. So in first condition, this data input means D input is 0 and our clock is also 0. So we will put D as 0 and the clock also at 0. So Q is the main output. Okay, so that's why our Q, we are getting it as 0. Here we are getting Q as 0. Okay. Then what they have done, they have changed this data input to 1. So if we change this data input to 1, so because this clock is triggering our D flip flop or D latch, that's why the output is not changing. Until and unless the clock becomes 1, this output won't change. That's why here our output is still 0. Clock is 0, so the output is also 0. So here what we are giving, we are triggering this clock. Okay, so if we trigger this clock, this output will change. So here we will put this clock to 1. So we can say this output has changed. Here the Q has become 1. So that's why we have put a 1 over here. Okay, here we are getting a 1. And again, if we change back clock to 0, so that is a memory state. So this won't change. Okay. So here DR still is 1. So, but if we put clock to 0, but so it won't change. So if we put back clock to 0, we can see it is not changing. Okay. That's why our D is 1 and the clock is 0. The output is also same. Then here we will put back this D to 0. So as our clock is also 0, so the output shouldn't change because that is a memory state. So already clock is 0. So our output is not changing. Then again we are giving a clock of 1. Again we will give a clock of 1. So again if we give the clock of 1, sorry, here I will do this part. First 0 0. So output we are getting as 0, then 0 1. Then also the output is 0. And if then we put the D as 1 and clock as 0, this Q remains 0. So we are giving D as 1 and clock is 0, then also it will remain as 1. Sorry. D as 1 and clock is 0. So D as 1 and clock is 0. So we are getting a 0. Then we will give clock as 1. So if we give clock as 1, then Q is changing. So Q is becoming 1. So here our Q is becoming 1. Then again, if we shift back to 0, it will remain constant. So again, if we put D as 0, so our Q will remain constant because that is a memory state. Okay. So again, here we have given the second clock. Uh, Clock we have kept it as, sorry, here D is 0. Okay, sorry, here D has become 0 and clock is also 0. So we are already getting a 1. Then we are giving this second clock. Okay. So if we give the second clock as 1, so, oh, sorry, if we give it as 0, if we give clock as 0, it remains same. It remains same. But here our D is 0 and clock will, again, we will give it as 1. So if we give it as 1, then our Q becomes 0. So this is what they have showed in timing diagram. Any doubt in this timing diagram? Any doubt in this timing diagram?
No, ma'am.
Okay.
No, ma'am.
So this is timing diagram. Just remember this: whenever there is 0, it won't change. Okay. First we will give 0, and then we will give 1. So unless and until the clock changes to 1, this output won't change. So wherever we will get a 1, this output is changing. Then again we are changing this D input to 0. Then also, if the clock is 0, it is not changing. But wherever we will give a clock as 1, this D input, it changes. Okay. So wherever here it is positive edge triggered, wherever we are getting a positive clock, there it is changing. So this is the working condition of D bistable state. The time truth table and a timing diagram. So here we are only giving clock as 0, so it is not changing. So that is a memory state. Okay. Here only clock 1 will work, and here we are not putting S and S bar. So only we are giving 0 and 1. So for 0, the S becomes 0 and R becomes 1. So the output Q is 0. So that's why we are calling it as reset. And for D input as 1, the S is becoming 1 and R is becoming 0. So the output Q is 0, 1 and Q bar is 0. So that's why we are calling it as set, because Q is 1. And if we change the clock back to 0, so that is a memory state. So this is the condition for a memory state. This D, it is not affecting. That's why we have given it as cross. Okay. So this is our D bistable. Then I told you the shortcoming of this D bistable, that we have like we can't do 1 1. This condition S and R, we can't put it as 1 1. So that's why, because of this drawback, we are introducing a JK flip flop or JK bistable. Okay. So what are the changes in JK bistable? To use this condition for NOR gate as 1 1, we are using this JK bistable. So it has two clock inputs. So we have two inputs as J and K. We have a preset and a clear present. Okay. We have two more inputs, preset and clear. And we have a clock input also. So here it is explained over here. So if JK comes in the exam, you can say this: two inputs are there, J and K, one clock is there, one preset and this clear is there, and two outputs are there. Okay. Q and Q bar. And you can also explain Q and Q bar can be complementary. Whatever you know, you just write it.
Okay, ma'am.
So here, how it is working. 1 minute. So here, first we will use this preset and clear. Okay. So this will work as first NOR gate, means first two bistable NOR gates. And then this is preset and clear, we are using it to start the circuit. Okay, so this is the enable pins. This is the switch of this JK flip-flop. So we will you see the first condition for this preset and clear. Then after it is switched on, we will start using this JK flip-flop. Okay, then this will become as SR latch. So this is one SR latch, preset and clear, and this JK is the second SR latch. So with preset and clear, we will work it, we'll use it as switch. So we will first start the preset and clear. Then if the condition is switched on, then we will start using this JK flip-flop. Okay. So we will first see how this preset and clear is working. So it will work similar as this NOR gate, RS NOR gate. Okay, it will work similarly. So I told you that NOR gate is the main. So every other output is depending on that output of that NOR gate. Okay. So here also this condition is invalid. Sorry, this we are using it as switch. So 00 is the memory state, but here we are using only as a switch. Okay, that's why we are not using at this memory state. So we will see this condition 01. So we will open our JK flip-flop. So here we have preset clear, here we have JK, J and K, and here we have a clock. Here we don't have an enable, but in the IC we are given a enable pin. That's why our circuit is working a little bit different. Okay. So for this condition 0, 1, so we will put clear as 0 and preset as 1. So we will put clear as 0 and preset as 1. So I think there is some so actually we are getting this as opposite. We are getting this as opposite because here you can see there is a bubble. It means it is negative edge triggered. Okay, this is negative edge triggered, but here in this part, this is actually our positive edge triggered. We can't see a bubble. If it was negative edge triggered, then there would have been a bubble, but because there is no bubble, that's why it is positive edge triggered. Okay, so this is coming like opposite. That's why this is coming as opposite. So for 0, 1, we are getting Q as 1, but you will just get the opposite for that. Okay, you will get a 1 over here. So that's why we are calling Q as reset. And for 1, 0, we will get a Q of 1, but here we will get a 0 because this is positive edge triggered and this is negative edge triggered because there is a bubble. Okay. So our system is working opposite. Here JK flip-flop is positive edge triggered. So if we give a 1, 0, then Q becomes 0 and Q bar becomes 1 because this is positive edge triggered. So for negative edge triggered, we will get a 1. So we will say that Q is reset. Okay. And here we can see for 1, 1, we are saying that enable the clock operation. So this is the enable condition. So if we do 1, 1, so that is the enable condition. It means that our system is switched on. But this is positive, this is negative edge triggered. So this 1, 1 condition will work. But here, because it is positive edge triggered, here the condition 0, 0 will work because that is just the opposite. Okay. So this here our condition will be 0, 0, and instead of that we have enable pin. So for this 1, 1 condition we will put enable as 1. Okay, only then this circuit will work. I will show you how this will work. Okay, so this is our JK flip-flop is getting switched on. So if we put this condition as 1, 1, our JK flip-flop is getting switched on and we will use this condition. So because this is negative S triggered, we will use the condition of 1, 1. And because this is positive S triggered, this is not in your syllabus. This is for reference, and here the IC we are getting, this is positive S triggered. That's why we are using a 0 0, and we also have an enable pin and we have to put it as 1, but here we don't have an enable pin. Okay, so this is enabling our circuit. So this is switching on our circuit. I will show you afterwards how it is switching on our circuit, this condition. So first our circuit is switched on by putting this preset and clear as 1 1. Then we will do the same thing for 0 0. It is working as memory state, so our output it won't change. And here we have a clock, so if we change the clock, our output will change. And then unless we put this clock to 1, the output won't change. Okay. So for negative edge trigger, we will put preset and clear as 1 1, and for this one is as a positive edge trigger, we have put it to 0 0. Okay, so first clock is 0, and we will put see this condition 0 0 is there, so nothing will change because this is a memory state for this. So we will see it afterwards. So if we see this condition, if we see the second condition where our j is 0 and k is 1, so it will work similar as our SR NOR gate is working. It will work similarly. See, if we put j as 0 and k as 1, so our output q is 0 and our q bar is 1. Okay, so output our q is 0 and q bar is 1, so q is the main output. That's why we are calling q as reset. Okay, then we will do the second condition, uh, j as 1 and k as 0. So we will put this j as 1 and k as 0. We can say that output is not changing. Okay, because we have to put a clock. So if we put a clock, we can see the output changes, and afterwards if we change the clock, the outputs remain constant. It means this is the main output. So q is becoming 1 and q bar is becoming 0. So our q is becoming 1. So we are saying that our q is set. Okay. And if we put this, so if we put back to 0 0, so that is a memory state. We will check this memory state. So if we put back to 0 0 and if we change the clock, so this output is not changing. It means it is the memory state. And if we put as 0 1 and we change the clock, we can see it as q has become 0. And if we change it back to 0 0 and we change the clock, we can see that output is not changing. So the 0 0 is the memory state. So here that's why we are getting a q. But previously we saw that for 1 1 this output was not working because it was invalid, but here we can say it is q bar. Okay, it means it will give opposite of whatever the q was. So if we do this jk as 1 1, so here we can see q is 0 and here q bar is 1. So here for 1 1 condition, we can see we are getting a q naught. Okay, so q is 0 and q bar is 1. So if we change the clock, we can see here we will get a 1 and here we will get a 0. So if we change this back to 1, so we can say that q is becoming 1 and q bar is becoming 0. Okay, so this is the previous state, and again jk is 1 1. So again if we change back to 0, it is not working, so that is a memory state. Then again if we change back this clock, so we will get an output of q bar. So this again it will become inverse. So we can see if we are wherever we are getting a giving a 1, it is like reversing because it is giving a q bar. Okay, so I told you this for this preset the output should be 1 1 for negative edge triggered, but because we have positive edge triggered, okay, we can say if we change this to any other state, And if we start changing the clock, this is not working. So this preset and clear, it is enabling this JK flip-flop. Okay. So here for positive edge trigger, the condition is 0, 0. So if we put it 0, 0, only then this is changing. Only then it will change. And if we put any other condition, you can see this is not working. So this preset and clear is working as a switch. So the condition for negative edge trigger is 1, 1, and for positive edge trigger it is 0, 0. So until and unless you put it to 1, 1 or in positive edge trigger as 0, 0, this clock it won't work. So you can see now it is working. Any doubt in this JK flip-flop?
Ma'am, can you explain it again, ma'am?
Okay, in JK flip-flop, what we have extra, we have JK flip-flop, which is working as a SR latch, okay? And we have a clock, which was we used in D. And here we have one more two inputs, preset and clear, okay? This is also working as SR latch or SR bistable. And we have two outputs, Q and Q bar. Okay, this you understood, this circuit?
Yes, ma'am. Yes, ma'am.
So actually what is this preset and clear is doing? It is enabling the circuit. So what is enable means? It means it will work as switch. Okay. The bulb will remain switched off until and unless you switch it on. Okay. So first you have to put a condition such way that this JK bistable, it will start working. So it will start working with a one condition when we put preset and clear as 1, 1. Okay. So first we will see, we will first switch on this circuit by changing this preset and clear as 1, 1. But here we can see, here we have a bubble. Okay, so but this circuit is a negative S triggered. Understood? This is negative
Yes, ma'am.
S triggered. Okay.
Yes, ma'am.
But here in this our circuit, this is actually positive. Here we don't have a bubble. If we have a bubble, it means it is negative S triggered, but we don't have a bubble. Okay, that means it is a positive S triggered and it will work opposite to negative S triggered. Okay,
Okay, ma'am.
this you understood?
Yes, ma'am.
So this will work same as NOR gate. NOR gate bistable, you understood now how it is working?
Yes, ma'am.
So it will work similar to that. So for this condition 0, 1, for 0, 1, actually this is negative edge triggered, so it will, sorry, this is positive edge triggered, so it will work opposite. Okay. So here we are getting Q as 1 and Q bar as 0. So here we are getting Q as 0 because it is working opposite. And if we do 1, 0, then here Q, this will become 1. But because this is positive edge triggered, here it will become opposite. This you understood, it is working same
Yes,
as
ma'am.
SRH. Yes. But
Now I
here we
understand.
can see this is 1, 1 is the clock. Okay, this will enable the pin. So if we do 1, 1, so here it will enable the pin. But because this is a positive S triggered and here because it is negative S triggered, our 0, 0 condition is the enable pin. Okay. So
Okay.
here 0, 0 condition we will put. But if it was negative S triggered, we have to put preset and clear as 1, 1. Only then our circuit will work. So it means,
Okay.
and here we have to put enable as 1. Then only our circuit will work. Rest you understood now?
Yes, ma'am. Yes, ma'am. Now I understood.
After switching on the system, then we will start using this JK. For others, I am telling. Then we will start this JK. So our condition is 1, 1. So this is how we will enable the circuit. And then we will do same how we did for SR latch. So for 0, 1, we will get a Q of 0 and Q bar as 1. Then again we will put J as 1 and K as 0. But this is not working because of the clock. We have to put back clock to 1 because clock is also enabling. So we will get Q as 1 and Q bar as 0. So the system is set, and this 0 0 is the memory condition, so our output will remain same. And here for 1 1 condition, here it is becoming q bar. So whatever the output was, it will just become opposite. So if we do 1 1 and we have to change the clock, so here our q is 1 and q bar is 0. So if we change the clock, we can say it is becoming just opposite. So we will keep this condition same, and if we change the clock, then you can see for 1 it is becoming opposite. So here preset and clear is working as switch. So if we change the condition to any other state, you can say this is not working. This JK, it is not working. So this preset and clear, it is working as a switch. Okay. So here the preset and clear should be 1 1. Only then our this JK flip flop will work. Okay, everyone, write your all numbers. Give the attendance. And you can leave. And I have updated the question paper, okay? That just see that whatever are the changes, those will come in the exam. Whatever questions have changed. I will discuss it on Friday, the question paper.
Thank you, ma'am.
Thank you.